So we just learned how easy it was to calculate the pH of a weak acid solution. We can apply all those same concepts to a solution of a weak base. Sometimes I think the hardest part is getting started with the equation, and they'll often give you the equation on the AP test. So we've got ammonia, NH3, and I think sometimes people's concern is it doesn't look like a base, NH3. But when it's in solution, it reacts with water. And if we remember the definition of a base, it's a particle that can accept hydrogen. It removes hydrogen from the solution. Well, where's it going to get the hydrogen from? The water molecule. One of these hydrogens will be attracted to the nitrogen of the ammonia. Because remember too, like the Lewis structure of nitrogen has that lone pair up on top, and then we can put the little hydrogens on for fun. This nitrogen end of the ammonia molecule is very negative. Not only is there a lone pair of electrons sitting there, but nitrogen has a really high electronegativity, so the electrons in those bonds are kind of drawn up toward nitrogen. So the nitrogen is very attracted to those little hydrogen atoms on the water molecule. So then on the product side, we'll be left with NH4 plus, the ammonium ion, and hydroxide. Oh, now I see the solution's a base. Hydroxide ions are produced. All right, so we're going to ice table again. ICE. Our initial molarity is, wow, 15 molar. That's like straight out of the bottle, concentrated ammonia solution. We don't care about the water. We could scratch it all the way through if you want. It's in the equation to show where the hydroxide is coming from, but we're not going to use the water when we do our equilibrium calculations because it's a pure liquid. We don't include pure liquids or solids. Initially, my products are 0. I know I'm shifting forward by x and plus x. So at equilibrium, I will have 15 minus x, x, and x. Okay, so they're going to give you KB values, or maybe in the homework they'll say look up the KB value on a chart. The AP test will just give it to you. KB is 1.8 times 10 to the negative 5th equals products, which is it okay if I just go x squared right away? Are we getting good enough that we can just recognize, oh yeah, it's going to be x times x on the top? And then on the bottom, I'll have 15 minus x. And are we getting good enough that we can just automatically think 5% rule? That k value is really small, 10 to the negative 5th. So whatever x is, it's also really small. Yeah, we're going to shift forward, but not by much. So it just really simplifies your calculation here. We'll cross multiply, and we'll get 1.8 times 10 to the negative 5th times 15, 2.7 times 10 to the negative 4th equals x squared. We'll square root both sides. X is, I'll go 3 sig figs to match the original molarity. 0.0164. Okay, so I'm going to think about the 5% rule. 5% rule. Check. That x is so crazy small. Compared to 15, there's no way that they would differ by more than 5%. X is crazy, crazy tiny. Okay, so you have a couple options here. Option number 1, x is the hydroxide concentration. So you could do this. You could go POH is opposite log of 0.0164 molar hydroxide. You could do that. Get a POH of 1.79. All right, that would be legit, 1.79. And then I could just do this guy. I could do pH plus POH equals 14. And then I would get my pH. And boom, I'm good to go. All I got to do is subtract from 14. This would make sense. It's a base, which I would expect it then to have a pH somewhere above 7. Maybe if we just go like 3 sig figs, I'll say just 12.2. So that seems reasonable. It's above 7. The other option, so I mean, pick and choose, whichever equation you prefer. You could do this. You could also do hydrogen times hydroxide, 6,4. There's the concentration of hydroxide. You could say that equals 10 to the negative 14th. You could then solve for hydrogen and then go opposite log. Either way, you're going to get the same answer. Totally up to you. Either is 1,000,000% legitimate. That's it. See, this really isn't so bad. There's nothing else that could make this more difficult. I mean, now when you get X is hydroxide. So if you know how to take the pH of a regular base solution, you're good to go at this point. The ice table just gets it to the point where we know the hydroxide concentration. So if that makes sense to you and you want to just shut me down right now, go for it. If you want to try this methylamine problem and then come back and see if you got it right, that would be fine too. Again, with this one, I think the worst part is just getting an equation down. And I mean, it's kind of a bummer. They don't give you the formula for methylamine. Obviously, they would, like on the AP test. Methylamine looks kind of like this. CH3NH2. In organic compounds, meth means one carbon. So you're going to have one carbon. That one carbon is surrounded by 3 hydrogens. And then amine means nitrogen. There's a nitrogen on the end. It's got a lone pair and 2 hydrogens. So again, like these nitrogen compounds often end up being kind of weak bases because they have the ability to attract hydrogen due to that highly electronegative nitrogen and a lone pair sitting on top. It makes that nitrogen group very negative. This will react with water in the same way as the ammonia. One of these hydrogens from the water molecule is very much attracted to that nitrogen. So on the product side, you'll be left with CH3NH3 plus 1 and OH. Hydroxide comes from the water molecule. So again, that's why they'll usually put the water in these expressions, these equations, because otherwise you don't really know where the hydroxide's coming from. It's coming from the water. All right, let's ice table. ICE. This one is a 1 molar solution. We're going to scratch the water all the way through. Initially, these are zeros. It's got to shift forward. We can't have zeros at equilibrium. Plus x. So we'll have 1 minus x, x, and x. These ice tables for weak acids and bases are so similar. Like really, you will be able to do these like in your sleep. What a sweet dream that would be, right? Okay, so Kb is 4.38 times 10 to the negative 4th. And I bet you're good enough, you probably just said x squared over 1 minus x. That k value is small, and it's small enough that I'm going to ignore x when I do my calculation. So I think whatever x is, it's going to end up being small. And that'll simplify my math big time. Because now if I cross multiply, well, this is easy. 4.38 times 10 to the negative 4th equals x squared. And then I can square root both sides. Let's take the square root and the square root. And I get x to be about, let's go 2 sig figs, 0.021. And again, x is very small. So if I were to plug that back in and say 1 minus x, that will differ by less than 5% from my assumption. In my math, I just used 1. X is small. 5% rule. Check. I checked it qualitatively. And again, it's always going to work because you don't have to use the quadratic on the AP test. Okay, so let's see what we got here. X is hydroxide. So I'm going to guess that maybe for a lot of us, this will end up being your equation of choice. POH would be opposite log of X, 0.021 molar hydroxide. And I get a POH then of about 2 sig figs. How about 1.7? And then all I got to do is subtract that from 14. pH plus 1.7 equals 14. Bingo. And again, I should check. It should be reasonable. Something above 7. Oh yeah, 12.3. That's reasonable. That's all there is to calculating pH of weak acid, or in this case, basic solutions. You do the ICE table to figure out the amount of hydrogen or hydroxide, and then bingo, opposite log if it's an acid, or opposite log of the OH to get the POH. Subtract from 14 if it's a base.